All right, welcome to Binary. By the end of this lesson, I hope that both of you will be able to read and write in binary and hopefully do a little bit of character encoding as well. So let's talk about counting systems. All right, so counting systems. Our counting system that we use most of the time is decimal. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. 10 numerals, and with those we can represent whatever number we want. But it's really important to separate a number from a numeral. 4 is a numeral. It's not a number. We can use it to represent a number, but we can represent the same number all kinds of different ways. And it doesn't change what the number is, only how we're choosing to represent it right now. So decimal is one way we can do that. Another common one we run into is hexadecimal. Hey, Augie.
Oh, I just wanted to pop in quick.
Good.
So are you saying that the number is like the mathematical value and numerical is like literally the thing that you write out?
Symbol.
Got it.
The
Okay.
number is the abstract concept. So like, I can say that I have two things without the numeral 2, and I can represent the two-ness of these things in all kinds of different counting systems.
Got it.
Hexadecimal is 0 through 9, and then A, B, C, D, E, F. And so the number after 9 in this counting system, 10, in decimal, that's 1, 0. In hexadecimal, that's A. They both represent the same number, even though they're different combinations of numerals. Roman numerals, another counting system, doesn't even use the same characters as this does. We end up with I's and V's and X's and L's and C's and M's. Different combinations of those numerals represent different numbers. And then we have binary. 0 and 1. There's no limit to the numbers that we can represent with binary. We just have a very small number of numerals that we can use to represent them. So the way this works, the way counting binary works, is with decimal numbers, we have like positions in a number, and they have like different values to them. So if I say the number 3,246, that's the ones place, that's the tens place, hundreds place, thousands place. So you do those multiplications, jam them all together. That's how we arrive at the number. Binary, exact same concept. Except it's ones place, twos place, fours place, eights place, 16s place, 32s place. So what we do is we look and see if there's a value in those places, and then we add them together. So this one has a 32, it has an 8, and it has a 1. So the decimal representation of that number would be 42. If we wanted to go the other way, we wanted to pick a decimal number and try to represent it in binary. Like, let's say I've got, I don't know, 71. With 71, we do the places first. Ones place, twos, fours, eights. And we keep going until we're like bigger than the number. Okay, so the next one would be 128. There's nothing in that place in 71. But there is a 64. You basically work left to right, and it's biggest numbers win. So we can't add 32 to it, we'd bust. 16, we'd bust. 8, we'd bust. 4, we can add 4 to it. So we end up with 68. 70, 71. Everything else is a 0. So that binary number is that decimal number. That's how you count in binary. Ask me some questions about it.
How does binary know where a number starts and stops?
Oh, I'm so glad you asked. So that comes from bytes. So in computer world, we're counting stuff. Actually, hey, before we get there, how come you think we use binary with computers? Why is that so common?
Because that's the only thing computers see is binary?
Wouldn't have to be that way. Actually, with quantum computing, we're kind of getting away from that even. It's not the only way it could be done with a computer. Sure is damn easier, though. Keep guessing. Why would binary be what we would reach for with computers, or honestly any electronics that need a
Well, I mean, a handsome genius once said that a computer is a rock that we taught to think. I could be completely 100% wrong, but data is just a bunch of switches, right?
Mhm.
And so, like, if you have just a series of switches and those switches are either on or off, then you could represent any data with any that amount of switches would be my guess.
Dope. Outstanding. It's really easy to make an analog for it. Yeah, switches are on or off. Then cool. Well, then these are just telling us which switches to turn on. Awesome. Here's how this has worked under the hood for a very long time. And if any of you mess around with Raspberry Pis, you can see this work at a very literal level. So we're passing voltage around through a circuit. What they wanted to do was whatever the voltage was, that was the number. And so if we get a lot of voltage, and say that's like a 9, and we get a little bit of voltage, and that's a 6, and a tiny amount of voltage, that's a 1. So it turns out, like in the 20th century when they were playing around with all this stuff, it was very hard to get something that would exactly do that. Because like, if you've ever fucked around with like amateur electronics, then you know, getting a precise voltage is, even in the modern age, kind of fraught with peril. So like this 9 could be an 8.9, and then it wouldn't be a 9 anymore. Or this 6 could be a 6.1 or a 6.2, or it could fluctuate a little bit and then end up being a different number. No good. So what we did instead is that if it's greater than 5 volts, it's a 1. Otherwise, it's a 0. That, like in the early 20th century, they could consistently do that. So presence of voltage, 1, absence of voltage, 0. Cool. Well, now that we can do that, it's almost like Morse code. We can send little pulses, and those represent data. Nice. Now, to that question we were looking at, how does it know where like the beginning and end of it are? Okay. So in some cases, it doesn't. Like with your internet, it's a stream of 1s and 0s. And then they get grouped together in things called packets, and that makes kind of the start and the end of it. But for most of the stuff that's happening inside your computer, these are organized in things called bytes. And a byte is 8 positions. So each group of 8 is a single number. Each one of these individual positions is called a bit. So we say that that's a bit. This is a byte. Cool. So we're pretty limited in how big a number we can represent, right? There's 1, 2, 4, 8, 16, 32, 64, 128.
I was going to say, so that you just can't represent 5 if you're just, or like 6, if you're counting the other way, right? So this is how you would represent like 5.
Yeah, so 5 is a 1 here and a 1 here. Yeah,
Oh, I
they're
see.
always they're bounded.
Right.
Byte is 8. So if we get a byte, we can figure out what number that byte represents. The challenge there is we can represent 256 different numbers with this. That's not that much. So we can also represent arbitrarily big numbers by saying like, well, we group them by larger counts of them. Like, oh, I don't know, 16-bit, 32-bit, 64-bit. That's how big a number you can represent in that system. And it's not like twice, it's not like a 1 bigger. When you add another one of these things, it doubles how many numbers you can represent, every single one of them.
Because it's based on another gateway further back.
Exactly. So this one, I can represent 256 different numbers. If I add another one to that, I have 0 through 255, plus, if that switch is on, another 256 values.
So if you have a series of numbers, how does the computer recognize like bytes, like multiple bytes? Like you're using parentheses here, but how does the computer do that?
With like memory registers. They're like in physically different parts of wherever they're being stored.
Okay, cool.
They're grouped that way in the computer.
And if you want to do like a decimal, like a float, then it would just be just a series of bytes, and then you would group bytes.
Float, you say? There's no decimals in binary. We use floats to represent decimal-y kinds of numbers. And so what you'd have, how you'd represent a float is you'd have the string of characters for that, and then you'd have another byte that represents where the floating point is, and that point can move.
Is that
Cool.
data type that I guess you'd be storing like the place of the decimal? Would that be like an enum? I think you mentioned that term the other day, where it's like kind of like an array where there's. Oh, never mind.
No, not necessarily. It is some data structure in the system somewhere, but like that gets encapsulated as, all right, here's the thing, here's the decimal place. You might also have one that indicates whether or not it's positive or negative. And so like all that combination of things together, you can get whatever number you want to represent out of it.
Okay.
Cool. So you want to figure out what a number is, or you want to turn a decimal number into a binary number. Write out the places, do the multiplication, and the things that have ones on them, add them up. If you're going the other way, you start with, you work left to right. What's the biggest thing that'll fit into here? And then what's the next one I can do without busting? And then you just keep doing that. Like, it's not immediately obvious. Like, this isn't an intuitive thing. There are no gaps in this. You can represent every single number, like in this case, between 0 and 127, in like a very ordered fashion. All right, cool. Time for you to practice. So I'm going to give you 2 binary numbers, and I'm going to give you 2 decimal numbers. I want to see if you can translate them. So we're going to do bytes on these. Cool. See if you can turn these binary numbers into decimal numbers. See if you can turn these decimal numbers into binary numbers. Go. Oops, sorry. Hang on. Fixing it. Yeah. Oops. Oh, you gotta be fucking me. Did it actually get rid of it? No. There we go. Ah, fuck, that's what it died. All right, shit. Sorry if you were already working through the second or third ones.
It's 20 or 26?
Oh, down at the bottom, it's 201.
201. Oh.
Another 30 seconds. All right, pencils down. Why don't you slack me what you got for those 4 numbers? All right, we got some disagreement. Let's work through it together. So if this is 1, 2, 4.
We can't see you.
Oh, no, you can't. $16, $32, $64, $128. Same down here. Just get these nice and labeled. All right, so here we've got a 1, an 8, a a 16, and 128. So $153. All right, for this one, we've got a 64, a 16, and a 1. That's 70, 81. Cool. Let's work it with these. 1, 2, 4, 8, 16, 32, 64, 128. 128, 64, 32, 16, 8, 4, 2, 1. All right, so 57. Nope, nope, yes. So if I do, come on, man. If I do 57 minus 32, now I'm trying to get to 25. Is there a 16 in that? Yes, there is. Now I want a 9. Cool. Well, I can figure that out from here. That and that. So there's my number. 201, you say? Is there 128 in that? You betcha. Okay, so I've got 201 minus 128. So now I'm at 73. Is there a 64 in that? Why, yes, there is. Cool. And now I want a 9. Well, I know how to make a 9. There we go. That is how you count in binary. Ask me some questions about it.
I mean, none of my questions are directly about it. My questions are more like, how does the computer know, like, when the color, when those numbers mean a color versus when they mean a number versus, you know, how they render. But as far as accounting in binary, I think that makes sense.
We'll talk about encoding next, and that might at least lead you down the right track for that. Other questions about how this works?
So you mentioned at the start of this lecture that a number is not a numeral.
Yes.
So if I had a float, like how? So I know that the computer is taking 2 bytes, and then one of the bytes is imposing a decimal on the first byte, right?
Correct.
So how does it then come up with the number for that, like the value? Because
Go ahead.
no, sorry.
All of that is happening at a way higher level than I think you think it's happening at. Down at the like beeps and boops level of your computer, there are no decimals. That's an abstraction that's happening way higher up.
Okay, thank you.
Like 99% of what your computer is using numbers for, like way down low, is, hey, where are we keeping this? They're like it's a phone book. They're addresses. You think of them more like indexes. Anything where you'd need to represent a decimal is usually happening significantly higher up than that. For example, C, like the programming language C, has floating point numbers in it. There's 2 levels of abstraction between that and the beeps and boops.
So is it fair to say that the lowest level is just an interpreter of the beep boops and just says like, here's the symbol that you asked for?
Correct. That is exactly it.
Thank you.
Other questions about binary? All right, let's talk about character encoding. So we can represent the numbers between 0 and 255, no problem now. We even get how these go from voltage into these. We're going to count off 8. And so like, and well, also with your computer, this is happening like on a schedule. So like every millisecond or like yotta second, every like some period of time, I'm going to check for the presence of voltage or not. And so like over time, that might end up being like 1, 1, 0, 1, 0, 0. So that's the voltage. 5 volts, 0 volts. So we get how we're doing that down at like an electronics level. We can organize those into numbers. So fucking what? Here's so fucking what. What if each of those numbers between 0 and 255 represented something? Like if I see a 1, maybe that's an A. If I see a 2, maybe that's a B. And, you know, 254 other things. Turns out there's just such a thing. Here's the first half of it, 127 different characters, and then here's the rest of them. So if you see a 1, that's how you represent the start of something. If I wanted to say A, capital A, that's a 65. If I want to say lowercase a, that's 97. If I want to say space, that's 32. Exclamation points, 33. So with each one of these characters, I can represent something. Now I can start writing words or instructions. And if I see certain patterns of these instructions, I could tell the processor to do something as a result. Now it'd be batshit crazy to like memorize the binary for all of that. But if you can type out some characters that you can memorize and it translates those into the little binary sequences, and those turn back into like hard-coded instructions for your processor. Add these two things together, store this thing here. Now we're programming.
One of my questions is just, it's more of like how the standardization works or whatever. Sometimes like I've tried dicking around and getting like a Chinese character or something like that, and then converting it to like a character number. Is that still technically ASCII convention, or is that just like maybe my MacBook has like a certain table somewhere where it identifies that as?
Thank you for the softball, John. So ASCII is where we start with this. It's not where we end with it, though. So like any HTML thing you've done with me, you've had to specify a character encoding because that's a required part of legal HTML. So you do meta, char set, What's the character set that we default to?
EN?
UTF-8.
Oh, UTF.
UTF-8. Cool. So let's take a look at UTF-8. Oh shit, there's a lot of these. Let's see. It just keeps on going. Look at all these things. All right, well, surely it can't have every character. How many UTF-8 characters are there? 2,164,864. Yeah, it can have every character. Also, all the emoji are all UTF-8 characters. Any guesses what that 8 is in UTF-8?
8 bytes?
8 bytes. 8 bytes to represent every character in UTF-8. And that's how many different...
Not 8 bits though, right? Like it's 8. So it's 8.
8 of these.
So that would be like 2 times 2. No, I'm sorry. 1 times 2 to the...
Here's a shortcut for it. So it's 8 here. We're talking about 8 bytes, so it's 64.
2 to the 64th then.
2 to the 64.
That makes sense. Different options. Sorry, I definitely messed up that logical spot.
No, that's one that it makes sense once you know it. You can't guess that. That's also a really good thing to know. You'll get asked like goofy computer science questions in interviews. That's like a good thing to know about binary. If you want to find out what the thing in red is at each of these positions, you count which position it is and raise 2 to that. Cool. So why did I talk about this ASCII shit first? See, 21 is an exclamation point. 21 is an exclamation point. Latin capital letter A is 41. Ooh, oh, there it is. I guess this is hex. Hex 41. Hex 41 is exclamation point, or is capital letter A.
So the UTF-8 is like a giant Rosetta Stone?
Yeah, it's exactly what it is. And the first 255 characters of it are ASCII. But once upon a time, we had ASCII, and then we extended it to UTF-8. There's also a UTF-16. And if you remember, that's not twice as many characters.
Like billions. More. It's more like billions.
Let's see.
Gotta be.
Does it even say? Looking for it.
Being 2 times 10 to the 16th.
John's on it.
Oh wait, no, it's not 2 times 10 to the 16th. It's just 2. Oh wait, it's 2 times 8. 2 to the 8 times 16.
I don't know. A whole shit ton.
Holy shit. 3.4 times 10 to the 38th.
Wow.
One of my questions about that is well, UTF-16, I'm assuming, is a lot more memory intensive, not
Correct.
memory storage. And then my question with that was, let's say I'm using Chrome browser, right?
Mhm.
Does Chrome browser know what UTF-8 is, or does it go to some external source to look up that information before it builds out your page?
That's a great question. Chrome knows what UTF-8 is. That's why you're telling it what your character encoding is.
Okay, so there's some stored version of UTF-8 on my Chrome.
Yeah.
And I'm assuming that's not the case with maybe other character sets, and that if you want to utilize that character set, it goes out to some source by default. And
It shows up as boxes, which I recently learned to have names. Name for boxes for bad encoding.
Is that related to emoji? The emoji part of that?
I don't know. I thought the square had a particular name that I'd never heard until recently. Name for rectangle. Yeah, this. Replacement glyph. Tofu, that's it.
Tofu.
Does they kind of look like blocks of tofu? Yeah, if your browser doesn't know how to do an encoding, that's what shows up instead. Cool. That's into our binary. Questions?
Do you know if the binary interpreter has a name?
Shoot. I don't. So at the lowest level, you're writing a thing called machine code. Let me find an example of it. Machine code looks like this. That's the thing right before binary. That's what assembly code is turning into. So assembly code looks like this. It's instructions to like the hardware on your computer for what to do. So that goes to machine code. Machine code goes to binary. Something like C goes to assembly. And something like JavaScript goes to C, C++.
And these are just like levels of abstraction.
Correct.
Cool.
Do you know if all computers share like the same assembly, or like would a Mac and a PC have different assembly languages?
The assembly is specific to the processor.
Gotcha.
So like Intel 8086 processors all have the same assembly.
Have you ever written that kind of code, like assembly or machine?
Fucking God, no. So like, and I think it's absurd that like anybody thinks that like app developers should do a lot of stuff with this. I think of it as the difference between making hammers and building houses. I build houses. I don't know how they make hammers. I don't know how they make saws. I don't know how they do any of that shit. I'm very proficient in using them. And I don't think that there's any expectation that somebody who's really good at making hammers is like a great carpenter. That might be the case, but I don't see any reason why those two things have to be the case.
If you wanted to make your own programming language, would you have to learn this stuff?
No, not necessarily.
Okay.
Like Yehuda Katz worked on Rust with Mozilla. I don't think he does any of this kind of stuff.
Interesting. Thank you.
Thank
But
you.
so-
Go ahead.
Well, so like the advantage of being able to like do like the assembly machine and all that kind of stuff is more like for people who are trying to like build more efficient processors to be like, oh, it uses X amount of whatever and keeps running with it.
Ding, ding, ding. So yeah, they're trying to figure out a way to do math faster. We're trying to find ways to build things that take advantage of the fact that we can do math faster. I can't. Okay, so I mentioned that quantum computing, this is getting back to like kind of the original idea of like, well, now we can do things that do precise voltages that we can rely on and stuff. So we can use like way more numbers at the like voltage level effectively. So that's cool. And there's a guy who's very active in the Denver community who does a lot of quantum computing. He works on quantum computing for IBM. And I kept asking him, it's like, cool, so what does that empower us to do? And he's like, I mean, you could do this stuff in fractions of seconds. It's like, awesome, so what? And like, I still, to this day, have never gotten a straight answer out of him. It's like, what new range of problems can we now solve now that we can crunch the numbers this much faster? I still don't know. Other questions?
So does that mean I can ask for an assembly class tomorrow?
Assembly class. All right. Thank you all very much. Hopefully this is useful for you. See you in
Thank
soon.
you.